thank you for the introduction and inviting me to give this talk. So before I start talking, I would like to say that, feel free to ask, stop me and ask any questions that you have during my talk. In fact, I would like that because that kind of gives me the energy to go on and, make the discussion more interactive. So with that note, I would like to talk about today about towards code aware AI models for code. So as we know, okay. So in present day, we know software is everywhere, right? And from the morning or even probably when we are sleeping, like we use some sort of software till the whole day and when we go to bed. So this huge and diverse type of software and the related industry is supported by relentless effort of developers who do different kind of job, like say first of course they code to build new software. After coding, they want to test whether that software is good, meeting the specification that they want to build. If not, they try to find bug. Then if bug is found, they do bug fixing, and finally they also have to write down some documentation which is explaining, most of the time explaining the high level specifications in natural language, right? So for this to support this diverse amount type and amount of jobs to software developers, um, over the decades, research and engineers are trying to propose different kind of tools and techniques. So some of these techniques are more technical in nature, like building like verification tools, testing tools, etc. Program synthesis tool which can automatically generate code. And then there are a lot of techniques that recommend best human practice. So for example, we know a lot of static and dynamic analysis tools that can automatically find bugs. We also know from industry and academia, there are a lot of tools, and currently, probably most of us use this GitHub Copilot kind of tool which can automatically edit code and generate code. Then among the best practices, to improve the quality of the code, researchers suggest that we should use assertion. Then there are a lot of team processes have been proposed, like, you should work in a more like you should do code review with your peers and things like that. However, in spite of all this decade of effort on how to improve code development as well as how to improve the code quality, we did this research in a few years back, where we took the top very popular projects from GitHub, which are written across like very popular 17 languages across 728 projects. And to our surprise, we found that 36% of the main branch commits are related to bug fix. So what does that mean? That if I assume that these commits are fixing actually some bugs, so roughly a large number of commits that are going to the main branch, right, after all this testing, etc. efforts, are still related to the bugs. And this is kind of not so inspiring story, because we took really high profile good projects like, Linux kernel, different kind of PHP, say compilers, etc., like very the code that everybody uses all the time. And even there, and they go through a lot of software engineering practices, and even there we notice there is so much bug coming to the main branch. And going a bit deeper, we found that, of course, there are a lot of reasons where the bugs are coming, because they are, like, say, for example, there are security vulnerability, algorithm concurrency, etc., etc. But the surprising fact is 88% of the cases, it is coming from pure programming error, like that developers I mean, make mistakes because of, like, just because of, most of the time, like, ignorance. So for example, typos, copy paste errors, incorrect error handling, incorrect API usage. So these are very programming related errors, and that are overwhelmingly dominating the real bugs that we found in GitHub. So this is kind of concerning, right? Because the software engineering research community and the people who develop the static and dynamic analysis tools, we kind of spend decade to basically guard ourselves to this kind of programming errors. And now, I mean, the reality is something different. So what is going wrong? Definitely research is not equating to the practice. And what we found, not only us, like many researchers as a whole, that though these different kind of tools are there, developers are often incorrectly use or underuse the utilities available to them. So for example, those who are familiar with, say, static analysis tool, you probably realize to use that tool correctly, you need a lot of expertise to first, choose the right kind of templates that static analysis will use to find bugs. So basically configuring these tools, using it requires a lot of expertise. So most of the cases we incorrectly use or underuse them. So again, this is another example where we make mistakes often. So in research, in industry, there are tools that can say automatically find bugs as well as fix them. So for example, template based bug fixing was very popular. And now let's have an example where I give the template, where I will, the template is that I will delete these lines marked in red, which is like return super dot equal object. And then I am going to replace it with the green line, which is return this equal to object, right? So this is the template I give. So the job would be of a tool would be to find these patterns that is marked in red, and then delete the pattern and replace it with the new pattern, the green line pattern. So template based analysis tool did great. It looked for this pattern, found it in the code, and then automatically replace it. Good, so job done. But now see what happens when in my code base there is a slight difference. So my template was to look for super dot equals. Now in my actual code, I have not equals. So the expectation would be, so not equals will be replaced by not equal. But because my template does not have this pattern, my template based tools will be failed to generalize in even such a simple scenario. So this shows the more traditional template based matching tools have low tolerance for deviation, and then you definitely cannot configure these tools with every possible patterns, because then in that case there will be too many patterns which is beyond even the knowledge of from the developers. So this shows the success depends on a lot of human judgment, and which is definitely not scalable and requires a lot of expertise. So now the question that we have to think that how to automate these different kind of tools that help software development better towards more better software development. So while this is a problem and we are trying to solve this problem to help software engineering development practice and code quality, I mean, we are seeing a huge boom of our availability of large software data. So with the advent of, and this is not even new, right? Like now with the advent of GitHub and then like Bitbucket and lot of open source forum, we have lot of software development code available. Not only the code, we can record different project related activities and archive it. So for example, what bugs developers are facing, the email and chat going on, user reviews, Q&A forums, etc. And they kind of encompass not only developers activity but many members of the software development tool like manager, project architect, tester, user, everyone, right. So now with the availability of AI machineries, what we can do, we can first archive those data, then curate and then process the data according to our need, then design a machine learning model which can learn from this data, and then a typical machine learning life cycle goes on, that where you will train the model with your for your purpose, and then that will eventually give us a AI based automation tool. So in such case, what happens, AI based modeling showed huge promise for automating different tasks like the task I just showed, because first code is very repetitive. uh, Many people showed that. And not only code is repetitive, the way developers do many stuff, say for example fixing bugs or writing bug reports, these things are super repetitive, and AI based models are usually very good to learn from such repetitive patterns, and then it can also generalize well where the patterns not exactly match but somewhat nearby. So this kind of software development practice opens huge potential for us to build AI based tools. Now while building tools, the tool like the famous tools like say Codex, GitHub Copilot, etc., etc., I mean they are usually based on natural language text processing tools. So they still treat the code as a natural language text. However, let's look back and think about what are some, I mean, properties of code that we know, like from traditional symbolic analysis or the code property logic. So first of all, there are some lexical properties, like we know the code has variable names, it has keywords like, operators and then identifiers, things like that. So for example, and here as you see that identifiers are also open vocabulary. So basically you can create pretty nonsensical identifier name, and that creates a challenge for any code modeling task. On top of that, code has rich syntactic structure, right? So even if I have this simple while loop, the abstract syntax tree that can be generated from this while loop is quite large, as you can see here. Further, the correctness of the program depends on its context, so and as well as the underlying language grammar. So for example, this code again looks somewhat like correct code, but if you pay attention, you will realize that I use a wrongly use if dot elements, but because if is a keyword in my language design construct, if cannot be used like a object or code variable, right? So this is syntaxically incorrect. The language grammar does not support this kind of code. Similarly, code correctness depend a lot on your context. For example, again here, this is apparently a good looking code, but notice that F is our function name, and it is very unlikely that it will be passed as a element dot equals parameter. Also, this function expects a Boolean return value. However, this code is returning null. And this kind of deeper semantic kind of analysis is, syntactic analysis is very difficult if you just treat code as a text. Also, as we know, code is not has deeper semantic meaning. So natural language by design can tolerate some semantic ambiguity. For example, if I say you a sentence, I saw a man on a hill with a telescope, this sentence has an ambiguity, right? We don't know whether you mean that did you use a telescope to see someone on the hill, or did you see someone on the hill holding a telescope? And natural language is perfectly fine of such open interpretation because it can tolerate ambiguity. In contrast, code has very structured and then, very constrained semantic meaning, right? If this while loop we are talking about, if we slightly change the meaning, the less than equal to, if we make like less than sign becomes less than equal to, the semantics will change and the code can output very different result, right? Similarly, look at we can change the code like from while x less than 0 to while z less than 0, as I showed here, though the structure changed, the code semantically is same. So without understanding this kind of deeper semantics, it becomes very difficult to reason about program. Further, if we go towards execution semantics, things become even more difficult. For example, if you look at the lower level code like the binary or your assembly code, they have these move, XOR, add, sub, this kind of instruction. And to analyze those programs, we need to understand what they mean. For example, if I look at this simple two-piece of binary, you will realize, those who are familiar with reading binary code or assembly code, that here in the first sentence, we are, in both the cases, the EAX register is setting to 0. And then in the first, we are adding 16 to 0. And we are, in the second case, we are subtracting minus 6 hex 16 to ex. So basically the output is same in both the cases. So these two pieces of code is semantically correct. But even if I ask a very sophisticated machine learning model to see or reason about whether these two simple piece of code is similar or not, they most likely will say they are not semantically same. So for example, here we ask ChatGPT, hey, basically whether these two code is similar, and ChatGPT, which is, we all know, is a super good, very powerful model, says basically no, they don't look like similar code, because the next one is setting the EX register to minus 22. The reason is that it does not realize the semantics of this instruction and how the value flows. So with that, and code also has some other extra properties like, say, bug reports, comments, etc., as well as diverse artifacts, code has this source code. It can be represented as source code, binary, execution traces, etc. So with these rich code properties, we should build code aware models that should understand the lexical properties, that should understand the semantics, the syntax, as well as the other kind of different representation of code. And not only that, code also changes over time, right? Because developers change code, incorporate new APIs, new features, etc. So code has a rich evolutionary feature as well. So our goal is to build model that is somewhat aware of these kind of code properties, and the way that it becomes almost standard way when we build machine learning model to first create a pre-training model. What pre-training model do? It first learn a generic code representation in a task agnostic fashion. So I give my corpus, code corpus, and build this semi-supervised learning using pre-training that just code representation. So you can think of someone. So, okay, before I talk about pre-training, there is a question. Would similarity between embeddings of the two code snippets show that two snippets are indeed similar? Yeah, so this is a good question, and that's how machine learning model perform. But that depends on how you are learning the representation, right? If I learn the representation just based on their token property, then the code embedding will basically capture their textual similarity. And even if the two code which look different, but which look different, but they are semantically same, then the code embedding will not be able to capture that because it is trained on only textual similarity. So this is what I am meaning, I mean, so far with this few slides, that when we are learning code embedding, we should embed the code specific properties so that the embedding can capture that, like the different type of code semantics. Amina, does that answer your question? Okay.
Thank you.
All right, great question. Thanks. All, like, please feel free to ask question. I mean, it will help me also to understand, I mean, or clarify points. All right, so we were talking about pre-training. So what pre-training usually do, it takes these different kind of code properties like lexical structure, semantics, and learn in a task agnostic way the code representation. So at a high level, what does that mean? Say I have a code written in Python, and I am teaching my model in general how a Python code looks like, or like C, Java, whatever language you are using, how in general that language, the code written in that language look like. So, and then once we have these in general pre-trained code representation, then you use that representation to fine tune or to customize your model for your particular task. And there are different kind of tasks where such code modeling shows promise, like, matching code similarity, like in more PLish term, it is code clone detection. Then code generation, as we see, like with this large scale model, they can now generate code very well, right? Then bug finding and many other tasks like malware detection. In all these different kind of tasks, we show a pre-trained followed by a fine-tuning model show really good promise. So the reason about this kind of setting is that the pre-trained model learn the key features like the program operation semantics to reason about program behavior. It generalize without any particular task, and then it can be adaptive across different tasks. Also, there is a cost thing. The pre-trained model is usually require a lot of data, so it is a kind of one-time effort. And for your individual task, you can basically take the pre-trained model, and with much cheaper smaller data set, you can customize it for your target task. So that's why this kind of pre-trained fine-tuning setting becomes very popular even while modeling code. So in while we talk about code modeling, uh, again, similar to the vision and image field, there are two kind of class of models that become popular or become effective. One is generative model, so where if you think about like vision, like you have these different kind of images, and you are learning embedding to generate say dog image and cat image, things like that, right? So very similar in code, we will learn embedding to generate the code. In contrast, there is a discriminative or classification kind of model, so which in vision field can distinguish between two pictures or two embedding, whether they are cat or dog. Similarly, here we can use a classification or discriminative model for code to say classify whether a code is vulnerable or not. So conceptually, again, very similar, but here, I mean, in code space, we are learning code embedding for different kind of code task. So with this kind of background of learning code properties using pre-training and fine-tuning, now I will talk about two particular line of work that we did, where we are leveraging, in one case we are leveraging static code properties, and in the I will briefly cover about how we can leverage dynamic code properties as well. So before I go deeper, any question so far?
Just to probe a bit further on that embeddings question. So I
Uh-huh.
think the claim of this, all these models that are training language and code together is there's some kind of transfer learning happening, and somehow languages are helping the models code better. And I
Uh-huh.
guess your claim is actually training code only models, perhaps with some prior knowledge about coding, do better. Is
So no, I am not saying that languages are I mean languages are not helping. What I want to say is that when the part of, like say nowadays the trend is that you consider natural language, text, code, all like similarly, right, with the similar modality, and then throw to this big language model and then do the downstream task. What I am saying, we can still do that. We can still use natural language and code as different modalities. But when you are treating code, use more code specific properties as well.
got it,
So that can be blended with natural language, which is perfectly fine.
got it.
Any other question? All right, so let's move on. So first we will talk about how we can leverage some static code properties, and I hope to kind of prove some of the questions that are asked, I mean, that you guys asked. So again, BART-like architecture becomes very popular everywhere, same for code. So usually we use masked language, build this stack of transformer, and then given a piece of code, we do mask language model. So basically we mask certain tokens, and then the job of this transformer encoder is to predict the missing tokens.
I'm sorry, we can't see your slides.
Sorry about that. So what I was saying, that we have this stack of transformer, and then the typically we mask some of the input, and the job of the transformer is to predict the masked input, right? And in that way we are learning basically the embedding of the code, where each of the tokens are treated more like a text, and we use very standard mask language model. So the question again that I want to ask here, that can such text-based model can accurately reflect functional similarity of the source code? So for example, let's take these two pieces of code. They apparently look very similar, but if you look more minutely, there is a subtle difference, which is I changed the float type to the integer type for these two variables. So the result in real code space is disaster, because this actually lead to an integer overflow vulnerability, which we curated. This example is real example that we curated from CV, like, which is common vulnerability database, right? So textual based model actually say that these two are exactly very similar code, and if it classifies the left hand side as a benign code, which is correct, it will also classify the right hand side code as a benign code, which is incorrect. It is actually a vulnerable code. Similarly, so code text cannot distinguish the inherent malicious functionalities here. Similarly, again, the same original example, if you take this one and you just change randomly the variable names, keeping all the functionalities same, the here these two pieces of code is not textually similar, but they are functionally identical. So if you want to do a code clone detection, most likely the model will say they are not cloned, which is incorrect. So again, this shows the code text cannot always reveal the inherent equivalent properties. So with this kind of understanding, we build this model using contrastive learning, where our goal is that we will take a original code and generates its deviant behavior as well as equivalent behavior with different transformation, and we will ask a model to put the two pieces of code which are functionally equal to be close in the representation space, and the deviant behavior to put far apart. And we use this kind of model for clone detection and vulnerability detection. So again, we have this original code. We inject bug to create a deviant behavior. We also synthesize clone with different kind of patterns. And then we have this pre-training I was explaining, where we are asking in the embedding phase to move the deviant behavior and original code apart and keep the positive examples closer to the representation space. So this is basically the training objective. And what we shows basically this kind of code aware training strategy can require significantly less pre-training data than the state-of-the-art baselines, and it also can achieve better performance. So what we did, again, we have this source code, we represent it in abstract syntax tree, then do static analysis, and then apply code different kind of code transformation to synthesize this bug or clone. So while synthesizing bug, we basically took many different buggy patterns motivated from the code vulnerability database. For example, we introduced misuse data type, misuse pointer, misuse variables, remove conditional checks, remove comparison operators, misuse values, etc. So again, these are very common reason to to have vulnerabilities in your code base. So we are doing data augmentation based on this domain knowledge. Similarly, for when we are synthesizing clone, we are using variable renaming, function renaming, statement permutation, etc. To have similar behavior, but the code will look different. So with this, we have this multitask pre-training, which has 3 heads. The first head is still our mask language model to understand overall how the textual property of the code. We introduce this green head, which understands the abstract syntax tree type of the each node. So that's how you can introduce syntax a little bit. And then the contrastive learning that I was introducing to somehow expose the semantics of the code. So again, in more theoretical form or equation form, we have mask language model to capture text, we have the tree type to capture syntax, and we have contrastive learning loss for capturing the semantics. And with this pre-trained model, we then fine tune for vulnerability detection as well as clone detection. And we check it with very well used data set that everyone is using for vulnerability detection as well as clone detection. So here is the result. At that point, like last year, we compared it with state-of-the-art models, Roberta, CodeBart, and Graph CodeBart, and we show that we achieve comparable results with slight improvement. But the interesting part is here. You see all the state of the art models are trained with much more data, which is like Roberta took 160 gig, CodeBart and Graph CodeBart took 20 gig, while Disco achieved somewhat better performance with even only 1.8 gig data because it already embed lot of code properties. So similar kind of result we got for clone detection, that with much less data, we can beat or perform equally with the state of the art models. So, which is great, which is very promising, but then we wanted to see the true potential of Disco. So we've increased the data size of Disco from 1.8 gig up to 13 gig, and we see constant improvement of Disco. And at this setting, in medium setting, which is still much less than the state of the art models data requirement, that we are comfortably beating or across all the setting the state of that performance. So here in a classification setting, hopefully now I can show you that code aware training makes much more sense and do the real improvement. But Disco is for classification or discriminative model. Okay, we have another question. So the static code models you described, do they tokenize like language models do, or do they operate on the input data as tokenized by AST? So as we have this text syntax and semantics. The text is the language model, same tokenization that we use in baseline, where syntax is the AST, like where we took this abstract syntax tree part. Okay, then can people, okay. Does the data size include augmentation? The data size, we have a setting where data size include augmentation, and even that it is much less, like much less than the like from 1 gig to 20 gigs. So it's much less than 20 gigs. So it's like say 3 gig kind of augmentation. All right. So okay, now I want to quickly show like how in the decoder setting or code generation setting, we can also do code aware pre-training. So here we have this, typical encoder decoder setting where okay. So here we took a correct code, we inject some noise to generate noisy code, and then this noisy code is taken by encoder, and the decoder's job was to denoise the noisy code to get back the correct code. So just to give a background, encoder decoder is a very popular way to train a model for code generation, where encoder is used for code understanding, as we see, and decoder is used for code generation. So we are still operating in the same framework, but here we slightly change the training objective. We make it a denoising encoder decoder, where noise is generated by the code aware transformation. So this is our code aware code property aware code generation model. So for example, here again we have original code. We make a loop transformation. So for example, changed while to for loop. Uh, we in another setting we did dead code insertion, uh, block swap, where if and else are swapped. We can do insert some confusing code, like say mid plus one is replaced by mid plus plus, as well as variable renaming, and then do this denoising auto encoder. And I don't want to go in details of this result, but just I want to show that even in, and we evaluated it across 7 languages for different kind of settings. So the generation task was text to code, which is a typical generation task. We also check code to code, which is a typical translation task. And then we have this mixed model where text plus code is input and it is generating code, which is a bug fix task. And across all these tasks, as you can see, I mean, again, you don't need to go through all the details, but high level is that NatGen performs better than the state of the art tools, which are mostly token based. Now, but most interesting part is here. When we use NatGen, which is this code property aware trained model, in a zero shot setting, we see that we are significantly outperforming Code-T5, which was the next best state of the art model at that time. So this kind of shows, without actually, if you have code aware pre-training, even if you don't fine tune with your task specific, say maybe you don't have enough data, or if you don't have enough resource, you can still use them for more task specific setting. And when you have small data, like in a few shot setting, um, NetGen can still perform better than Code-T5, but Code-T5 is slowly catching up because you are exposing it to the with more task specific data. But here it shows like when Code-T5 will catch up eventually, and across all the setting you can see that eventually after say 500 ish kind of data sample, Code-T5 and NetGen kind of started merging, but still, I mean, Code-NetGen is still perfectly I mean strictly better than Code-T5. So hopefully with these two work, I can show you we just leverage at a high level code semantics and syntax properties, and we can beat a text-based model for both classification and generation task. So I want to quickly cover, like in 2-3 slides, that so far we are talking about static properties in details, but dynamic properties also help, and the help is even profound. So we know that for vulnerability detection and many other tasks which need deeper semantic analysis, we need this kind of examples, like for similarity detection, where we need to understand the code properties. And I was showing this ChatGPT example as I was showing before. So without exposing the model to these dynamic values, it is almost impossible to figure out that what is going on semantically. And these are important because in binary, the code may look very different across different architecture, across different optimization flag, also when the code is obfuscated. So any kind of deeper security analysis requires more deeper program analysis and you need to understand what kind of values are flowing, what is the execution, etc., across apparently not similarly looking code. So only static analysis can definitely cannot give us a good result here. So what we did, again, very quickly, I would be happy to talk in details later. We basically randomly initialized code with different values, let them run, and at a local context, we generate trace and understand what the code looks like. So again, given a binary code, we have this instruction sequence. Then we added it with other dynamic value properties like trace, memory address, control flow coverage, whether, so that means whether this branch is executed or not. So we have basically these four modalities. One is static code, execution, trace, memory layout, and control flows. And we have some additional auxiliary annotation like the positional encoding as well as the which architecture this particular code is using. So with this, we again build a transformer specific self-attention kind of models. We also uh, design our masking in a more intelligent way, where we are basically teaching the model what kind of operations each of the instruction is doing. Like if it is 2 minus 1 and we are asking to predict the value, we are teaching the model basically subtraction operation in both like right hand side and the left hand side way. We are also teaching slowly model with multiple kind of operations and increasing the difficulty. So with this kind of scheme, we showed that across many deeper program analysis tasks, we perform better. So for example, semantic load detection, we perform 14.3% better. Type inference, memory dependency analysis, which is a notoriously difficult task, where we perform 52.6% better than the traditional program analysis techniques. And remarkably, they can do it in a much faster speed because now we have this machine learning pre-trained model. You do little bit fine tuning and then basically it is one shot query, right? So the speed is significantly better. So, and this kind of training remains robust across compiler, different kind of compilation, architecture, optimization, obfuscation, etc. So again, quick summary, the dynamic code properties also help a lot, especially if your task is require much more deeper understanding. So I have a question. So is this pre-training also applied to source code rather than assembly code? That's a very good question. So this work we mostly apply to binary code. In source code, it becomes, and we are currently the applying to source code is current ongoing work. But from our initial set of experiments, what we realize it's a little bit tricky in source code because often you have objects and like other kind of high level types, right? And how to flatten those high level types with a deeper semantic representation, that becomes challenging. So we are working towards that. But short answer is yes, and there also we show we can see pretty good improvement. But I feel, we first tried in binary, and which was much easier things to do. Okay, so yeah, so with that, with a quick summary, we talk about uh, like how we can do how we can capture static code properties for both code understanding as well as generative task. And we also show dynamic code properties for code understanding. So the next question is what next? And AI powered, we all know, right? AI powered coding assistant is knocking at the door, like with Copilot and other competitive tool. We are probably using it, a lot in our everyday practice. However, they don't come with any guarantee. So in spite of all these hype, several controlled studies in lab showed basically this kind of, the people don't trust the code that is generated by these AI assisted tools in real software development. So they use it, but I mean, they use it as a reference, like how we used to take Stack Overflow code, but then, go through a lot of scrutiny and then adopt it. So then eventually trust becomes a big issues and will become a big issues. So I think when we think about AI powered code analysis, we have to also think about how to improve the trust. And we know traditionally we develop, like as a community, we develop lot of formal analysis which gives lot of guarantees, but they are noise intolerant. In contrast, probabilistic models like AI powered models are scalable, transferable, but they do not come with any guarantee. So I feel, or I think, is a good model eventually will reach a middle ground where we will have more guarantee with developer feedback, code property. We should also incorporate explainability, and with that we can build this holistic, more code aware model, which can eventually be better, will increase developers trust, and can make that whole development life cycle much better. So with this, I would like to thank all my collaborators and students. Without them, this work would not be possible, and I am ready to take some more questions.
Robbie from University of Michigan at Dearborn. I have a question for you. So what's your experience in terms of more algorithmic transformation? Like if you have an inefficient algorithm and want to transform it a more efficient algorithm, is it possible?
So yes, I mean, so we call it refactoring, I mean, in software engineering term, and I think this will be very much possible. In fact, given there are relatively few rules to make a algorithm possible, actually, if we do more targeted, if we expose the model with such more, transformation, like how to say make a more performance efficient code with a little bit more this kind of targeted data, I think it will be possible to improve the performance of the code. But
Right.
here the strategy will be to augment the data in an intelligent way, the kind of way you want to reach there.
Right. And another question is that when you are training the models, did you consider using graph neural network? Because generally the code are tree-based structures, right?
So yes, as my first work, sorry, again, the first work where we are using comparing here, where see the graph code part is basically using graph structure, somehow using graph structure. So again, it is only syntax, and where we are using both syntax and semantics, and we show syntax and semantics is somewhat better than only graph structure.
Right.
But another thing, actually, we overall realize, I mean, over the time, transformer is actually can capture a lot of this data and control dependency. So though you are not explicitly giving a graph structure, if you are using transformer, you somehow leveraging the more this graphical behavior of the code. So that is also there. And that's why in most of the task, right now, transformer kind of architecture is winning over graph-based structure.
I see. Another thing is that is it require a lot of more training if you are using transformer than using graph structure?
No, not necessarily. We were talking about pre-training because we wanted to learn a general purpose representation that can be used for different tasks. But say here again, that slide it is showing now, the graph code but is a transformer structure, and graph code but is not exactly graph neural network, but use graph structure, and they take similar kind of like training resource.
All right, thank you so much.
I can see a hand raised by Rafael.
Hi, I'm Rafael from Slovenia.
Uh-huh.
I'd like to ask, first of all, thank you for the lovely talk. You've outlined a lot of details and it's been very educational. Have
Thank
you
you.
published any of the models you described, like the pre-trained and fine-tuned? Are they available to use at home?
Yeah. So all the models that I talked about are open source. And if you, I can share it with you if you send me an email or something.
All right, thank you so much.
Any other question? I don't see any hands or chat.